Happy New Year. Welcome to Differential Equations here. I appreciate you taking the class. Derek, welcome in. It's good to see a lot of folks. I think everyone in chat right now is a former student of mine, either from last semester or before. If you're new to this format, I do have a separate monitor with participants in the chat window open. So if you have questions, you just go ahead and type it in that chat. Or if you want to, you can unmute. That's all good. All right. The prerequisite for differential equations a few years ago was dropped to Calculus 2. But there is a little bit of multivariable calculus you need that we'll be using here in the in the first unit, and that's partial derivatives. So we're going to review the mechanics of partial derivatives. For the whole story of partial derivatives, you can email me. I can send you a link to the lecture on it if you want. But usually this quick review here at the beginning is enough to get us going for what we need out of them here in DiffEQ. All right. Hopefully you watched the welcome video. Once again, if you have any questions, just feel free to email me. Every office hour that I have will also have this WebEx open as well. So you can always tune in to office hours and ask me questions. All right, let's quick review here of derivatives. The derivative of a function, f prime of x df dx. What we're looking at is we're looking at the change in the function divided by the change in x. So the change in the outputs over the change in the inputs. And then we take a limit as the delta x goes to 0. That gives us our instantaneous rate of change of f with respect to x. That's our derivative. If you have a function of more than one variable, then we can do the same thing one variable at a time. That's one of the big themes in Calc 3. So if you notice here, this notation, the partial of f with respect to x, welcome in, Cole, fx, we're still looking at the change in the function, but notice we're only changing the x. This is the change in the function divided by the change in x. We're treating y as a constant. We haven't changed the y at all. Welcome in, Tim. That's the partial derivative of f with respect to x. And then you can do the same thing, looking at the change of f with respect to y. Notice here the x is the same, so we haven't changed the x at all. And so computationally, if you're looking at the partial derivative of f with respect to x, you take the derivative treating x as a variable and you treat y as you would any other constant. To take the partial derivative of f with respect to y, you treat y as a variable and treat x as a constant. So once again, if you had the Calc 3, this should be old hat by now, but if you haven't, if you're coming in from Calc 2, you might want to practice this. So let's take a look at this function here, f of xy. It's a function of two variables. So you want to take the partial of f with respect to x. That means we're going to take the derivative with respect to x. We're going to just treat y as we would any other constant. And all of the properties of derivatives still apply. So your sum and difference rule, your product rule, your chain rule, all that stuff carries over. So let's go ahead and just start a new page for this. All right, so all the derivative properties apply. What would be the first property we could apply here to get going with this derivative? That was the cat's answer. So we got our sum and difference. And now since we're taking the derivative with respect to x, we're treating y as a constant. So The constant multiple rule says you can factor that 3 out front, but since we're treating y as a constant, it comes out front as well. So we can just do that. Oops. And now we're taking the derivative of the cosine of something. So we can use the chain rule. The derivative of cosine of something is the opposite of sine of that thing and then chain rule kicks in times the derivative of that thing with respect to x. So now we just got our classic power rule here. And now we're taking the derivative of x times y with respect to x. Once again, we're treating y as a constant, so I could factor that out times the derivative of x with respect to x, which of course is 1. And so my final answer would be 6xy plus y sine xy. So if you are new to this concept, we'll do one more of these. We'll do a partial with respect to y. Any questions on the calculation there? So once again, if this is brand new to you and you want more of a story, just let me know. I'll just fire you off the video from one of the several videos I have recorded of talking about these things. Okay. Let's calculate the partial of f with respect to y. It's 3x squared y minus cosine xy. Once again, all the properties of the derivative are in place here. We're taking the derivative with respect to y, treating x as the constant. So we start the same way as before. We hit it with the sum and difference property. Bless you. Now, the x and therefore the x squared are considered constants. So we can factor these out front. And now once again, I'm taking the derivative of cosine of something. So that's minus sine of that thing times the derivative of that thing. Whoops, derivative with respect to y. The derivative of y with respect to y is 1, so that's a 3x squared. Minus a minus is a plus. Sine of xy. And once again, here we're treating x as the constant. So I could factor the x out times the derivative of y with respect to y, which is 1. And so we get our final answer here. And that's the partial of f with respect to y. Okay. So whether or not this is new or hopefully a nice refresher for folks, any questions on calculating these partial derivatives? I think pretty much everyone in chat had the Calc 3 already. But as usual, half the students are going to be watching this video later. Because I think there's a fair amount of overlap with one of the physics classes. Actually, there you are. Okay. Here's an example you can work through in the privacy of your own home. This is about the ideal gas law. PV equals nRT. Solve for P, find the partial of V with respect to V. And so you got the answers here to work through on your own. And then you can actually prove this very important thermodynamic property. So this is apparently a characterization of a system like this. And this is also an example of why you can't treat these as fractions. Because if you treated these things as fractions, everything would cancel out, right? And if these were really fractions, what would this equal, folks? Yeah, it'd be equal to 1, which it doesn't. It equals -1. So just treat them as fractions. Well, sort of. All right. Now, we are going to have an occasion next week to look at the partial derivative of something with respect to y. But where we are really going to be using the partials this week is in this formula for implicit differentiation. So if you have a curve, f of xy equal a constant. So basically, if you've got things arranged this way, you got a bunch of x's and y's over here equal to a constant, then you can actually find the ordinary derivative dy dx implicitly using this formula. All right. We're going to be using this over and over again here this week. So for example, if you look at this curve we've got here, x squared plus 2xy plus y cubed equal 9, you can view the left-hand side of this equation as a function of x and y. And in Calc 3, the graph of this function ends up being a surface in space. When I set this equal to a number, I'm looking at slicing that surface at a particular altitude, and I get that contour. And so this results in a two-dimensional curve. And if things are nice enough, locally, that two-dimensional curve, I can express y locally as a function of x, and you might want to know what dy dx is. So this is the same kind of implicit differentiation idea we had way back in Calc 1. It's just we can use Calc 3 to help us calculate it much more quickly. So this is something you prove in Calc 3. Once again, if you want to revisit how that works or anything, just let me know. I'll send you a clip of the video there. But basically says that to get the dy dx, it's minus the partial of f with respect to x divided by the partial of f with respect to y. So if I look at fxy here, x squared plus 2xy plus y cubed, I'm going to go ahead and get my fx. Fx is another way to denote the derivative with respect to x, treating y as a constant. So we've got our sum and difference formulas in play, we've got our constant multiple formulas in play, and we got the power rule in play. So if I'm taking the derivative with respect to x, the derivative of x squared with respect to x is just what? That's just your 2x. Plus, now here, I'm taking the derivative with respect to x. That means I'm treating y as a constant. So if I just had the derivative of 2x, it would just be 2. In this case, I've got 2xy. You treat the y just like that 2. That's your 2y. And if we're treating y as a constant, then y cubed would also be a what? It'd also be a constant, so its derivative would be 0. Okay, so that's fx is just going to be that. And then fy, I do the same thing, except now I treat x as the constant. So once again, if x is a constant, so is x squared. The derivative of that with respect to y will be 0. What's the derivative of 2xy with respect to y? So what would the derivative of 2xy be with respect to y? Good, that would just be the 2x. And then the derivative of y cubed with respect to y would be usual 3y squared. And so if I wanted to put this together, I would have minus. The numerator would be the 2x plus 2y The denominator would be the 2x plus 3y squared. Boom, there's dy dx. Okay. Find dy dx for the family of curves x squared minus y squared equals c squared. What restrictions are needed? You remember what these look like? Those are some classics. Anyone happen to remember what x squared minus y squared equals c squared, what they all look like? If you don't remember, we got Desmos. Desmos is back. Yeah, they're well, hyperbolas, because we're two-dimensional right now. We're back in the plane, but yeah. We can just put that in, c squared. We can add a slider for c, and we can see it. Now when c is 0, of course, we boop, get intersecting lines, but yeah. Here's your hyperbolas. And we're going to be using Desmos again, well, two-dimensional Desmos, when we graph solutions to these diffie-qs and things like that. So I'll leave this to you here. Remember, you want to get everything f of xy equal a constant. So in this particular case, you just got the x squared minus y squared. You go through the shenanigans, you're going to get dy dx is x over y, as long as the denominator isn't 0. And if we look on the graph where y equals 0 on the graph, that's going to be at these intercepts here. Thank you, Desmos. What kind of tangents do we got there, actually? Technically, we do have tangents, but they're what? Oops. What kind of tangent lines are at when y equals 0 on these things? So dy dx does not exist, but we got vertical tangents there. All right, so we're 15 minutes into the course. Well, 20 maybe. Finally, we're going to get to differential equations, right? So we got some terminology. A differential equation, which we'll abbreviate as DE, is an equation involving a function and one or more of its derivatives. So here's a differential equation. Here's a differential equation. And here's a differential equation. You've got functions. In the first two, the functions are y. Here it's very clear. Y is the dependent variable, x is the independent variable. So we got a y equal f of x kind of a situation here. Here it's unclear what the dependent variable is, but y is definitely the dependent variable. The independent variable, it could be x, could be t, could be anything other than y. And what's going on here, once again, if you haven't had the Calc 3, these are partial derivatives. So here we've got a function u, which is a function of both x and t. And we got a partial derivative of u with respect to t. Here we have a second partial derivative. Does anyone happen to remember? This is a stretch. This is a stretch for sure. Does anyone happen to remember what kind of equation this, what phenomenon that kind of equation models? This is no, not wave. You're close, Zoran. Wave has second partials in both. Oh, this is actually the heat equation, but Zoran, you get partial credit because that's close. We had the heat equation, the wave equation, and the Laplace equation. But yeah, so this is your standard equation more generally for diffusion. If you got something diffusion through The partial with respect to time is directly proportional to the second partial derivative in space. Okay, there's two main types of differential equations. You've got an ordinary differential equation, ODE. That's a function when you have one independent variable, so these would be ODEs. This is what we're studying in this course. If you've got partial derivatives involved, that's a PDE, partial differential equation. There's a course on partial differential equations. I took this course. I loved it. This course, you do so much cool stuff in it. One of the cool things you do in it is linear algebra, which I don't know if any of you are taking linear this semester with Dr. Paul Zachlin. Linear ran. Calc 3 did not. Linear and DiffEq ran. If you're taking linear and DiffEq at the same time, it should be a treat, because we will be using the same big ideas throughout the course. Linear algebra was the course I took that made me a math major. That's when I decided I really liked math more than the other stuff I was working on. The order of a differential equation is the highest derivative. So, you talk about like the degree of a polynomial is the highest non-zero power of x. The order of the differential equation is the highest derivative that you see. So we're going to be spending a lot of time here on first order differential equations. This is pretty much chapter 2. Chapter 2, 3, and 4 are on first order differential equations. Here are some second order. Since we've got a partial here, we look at the highest order of the partial. So order is the highest derivative in there. Now, fun fact, you've actually been solving differential equations the whole time. So for example, what's the integral of 2x dx? This is one of the very first integrals you did. You could even do this one geometrically, or you could do it as a Riemann sum. But what's that work out to be? Yeah, x squared plus a constant. Now, you can think of this as solving this differential equation. You're looking for solving y prime equals 2x. So to undo that derivative, you would take the antiderivative. You would integrate. And so this actually showcases a lot of things we're going to be seeing throughout this semester. First off, we add that constant c. That's courtesy of our mean value theorem. Because we know as long as we're on an open interval, every antiderivative of a continuous function is going to be off by at most a constant. So technically what this would be called is this would be called a one parameter family of solutions. And the term that we tacked on has the property that when you take the derivative of it, you get 0. So when you take the derivative of the x squared plus c, we've got this part, what we call a particular part. This is a particular term. That gets you to the 2x part that we want. And then the constant ends up going to 0. So this is a solution to the derivative equals 0. And so we're going to see, as we move through the course, this kind of a structure. If we have sort of a part that works, and then we've got a part that we tack on whose derivative somehow is going to 0 out. All right, so we're going to see this sort of breakdown into a particular part and what's called a complementary part as we move through the course. A solution, so this is the book terminology here. So we're using this book. Hopefully you saw the link to it. A solution to an ODE is a function which satisfies the ODE in an open interval AB. The largest open interval where you have where the solution is valid is called the interval of validity. A solution curve is the graph of a solution, but an integral curve is the graph of a curve that you can restrict to give solution curves. All right, so once again, this is the textbook terminology, the textbook we're using. So every solution curve is an integral curve, but an integral curve may not be a solution curve. So as an example, x squared minus y squared equals 1. You can go through, and this is the example, one of the examples we did, or I mentioned earlier here. You can go through, you can check with implicit differentiation that dy dx is x over y. So that means that the x and y on this curve satisfy this relationship, provided y isn't 0. And so the way the terminology works, let's just put that as 1. The way the terminology works is that this would be an integral curve for the differential equation y prime equal x over y. This curve itself, though, does not describe y as an actual function of x. So solution curve, whoops, if I could spell. What you do is you'd have to take part of this defined on an open interval. So for example, if we start here and we take one of these branches, we can't include this point because the function is not differentiable there. But for example, one solution would be y equals the square root of. So I could solve that for y. So I could do y equals the square root of x squared plus 1. For x strictly bigger than 1, that would be a solution, and that would be the corresponding solution curve. You could go over here if you wanted to and pick this one out. Another solution would be y equals minus the square root of x squared plus 1 for x strictly less than negative 1. This would be another solution, and the graph of that would be the solution curve. So integral curve, you can go into the integral curve and find solution curves in there. Solutions, though, are restricted to being differentiable functions. So they're functions that satisfy the differential equation on an open interval. All right. So it's just a little, some technicality there. Do you understand the difference between the two? No, it would, if you look here, Tim, if you solve it, you'd add the y. Oh, yes, it is x squared minus 1. I apologize. Thank you. Thank you, Tim. These would be all minuses in here. Yep, thank you. Okay. So any questions between the integral curve and the solution curve? Anytime you see the word solution, you need a differentiable function and you need an open interval. Okay, so you need an interval that looks like this. Okay. Example, find solutions to y prime equals x e to the x over 2 and the associated intervals of validity. This is just a review of integration here. So to undo this derivative, we would integrate. So I'll leave you to do that. This would be a good one for tabular integration. tabular integration is going to come in handy. So when we get to it at the time, I've got a little refresher built in for you on that. Okay. So as I kind of mentioned a little bit ago, this C here, is we have infinitely many solutions, but they're all off by a constant. So this is called a one parameter family of solutions. The word parameter here refers to the choice of the constant C. So you have one choice here. You can pick C to be whatever you want. That's going to give you a different solution. And thanks to the mean value theorem, we know that every solution to this problem on this interval is going to be off by a constant. And that makes this what we call the general solution. So the general solution means that every solution is obtained by a particular choice of parameter. In a general solution, it's like Pokemon. You got it. You caught them all. Okay. The general solution contains all the other solutions. Okay. And this is going to be our goal here in differential equations, is to find the general solution. All right, so here's an ODE. dy dx equals y times 3 minus y. It's an ordinary differential equation because we've got an ordinary derivative. Here we know that y is the dependent variable. We also know that x is the independent variable. It's a first order equation because that's the highest order derivative we have. We're asked to verify that this is a one parameter family of solutions. So the one parameter part corresponds to the fact that we have this constant C, and it's the same C in both places. So there's only one parameter here, and that's this one constant C. We don't have a C1 and a C2. We just have the C there. So if we want to show that this is, if we want to verify solutions, and this is important because this is pretty much your first test and first take home, which we'll talk about either tomorrow or Thursday, involves a lot of verification. All right, verify, verify, verify. The way you verify something is you start with what they give you and you plug it in to see if it works in the differential equation. So the first step to verify would be to take the derivative of this with respect to x. Now, what could you do here to help you simplify taking this derivative? So what could you do here? Do you have to bust out the quotient rule? Yeah, we could rewrite this. We could rewrite this as 3c times the derivative of c plus e to the minus 3x all to the minus 1 power. So we can use the constant multiple rule and the power rule here. So this would be 3c, the derivative of something to the minus 1 power. And then chain rule would kick in. And folks, what's the derivative of c plus e to the minus 3x with respect to x? What's that going to work out to be? Yeah, good. Minus 3 e to the minus 3x. So if I'm going to have this multiplying all of this stuff. I've got a minus 3 times a 3. That's going to be a 9. C e to the minus 3x times c plus e to the minus 3x to the minus 2. So that's dy dx. Now to verify that this function is a solution to the differential equation, I now need to compute the right-hand side and see if I can get it to match the left-hand side. Okay, so now I'm going to look at y times the quantity 3 minus y. So I'm going to plug this in. So 3c over c plus e to the minus 3x times 3 minus this. And now I'm going to do some algebra. So I can get a common denominator. So I'm going to keep this out front here. So I'd have to multiply numerator and denominator here. And I'm going to simplify. So I've got 3c plus e to the minus 3x. And now that I've got the same denominator, and go ahead and subtract the numerators. And you can see, pun intended, what happens to the 3c's. They're gone. Oops, I forgot a 3 on this one. Multiplication there. So now we can see what we got. We've got a 3c times 3e to the minus 3x. So that would be multiplying what survives in there. And then I've got that on the bottom. And then I check, is that the same? Right? So I check, is that the same as what we got for dy dx? And so we go back, look what we got for dy dx. And sure enough it is, right? It's just written slightly differently. And sure enough, that works. Okay? So when you see verify on this week's take-home and test, that means you just want to plug it in and check. Just like when you check your answer to an algebra equation, you plug the thing back in and see if it works. Now, is there a way to, this is what I'm looking for. Now, can you check answers using Desmos? Because we did that a lot in Calc 3 and Calc 1 and Calc 2. Yeah, you actually can, as long as you type things in as f of x. So let me show you how you can check these equations on Desmos. You want to write your y equals f of x. So we would go f of x equals, and then you would do the 3c. Excuse me here. So 3c divided by c plus e to the minus 3x. And go ahead and add that slider c. When you do that, you can see, pun intended, what these things look like. Does anyone remember the name of this kind of curve? For these kinds. There's a particular name for this kind of curve here. Do you remember what that is? Yeah, log of something. Great. Yeah, it's actually called the logistic curve. Very good. This is called the logistic curves. These are very important. We'll be talking about these, next week maybe? Yeah, I think next week. Anyway, there's logistic curves. Now, I want to show that it satisfies the differential equation. So what I'm going to do is I'm going to drop this off, and I'm going to graph f prime of x. And then I'm going to graph this, f of x times 3 minus f of x. Can you tell the difference? There you go. Yep. Yeah, it looks normalish. Anyway, that's how you can check these things graphically. And we'll be doing more of that next week. Okay. So let's take a look at this one. Verify that y equals 3 is a solution to this differential equation. All right, so this seems a little anticlimactic, but it's the end of the class. So they're looking at y equals 3, so we have to check, does dy dx equal y times 3 minus y? Whoops, I gave it away. Okay, well, if y equals 3, what's dy dx? What's the derivative of 3? 0. Is 0 equal to 3 times 3 minus 3? You bet it is. So y, in other words, f of x equal to 3 is also a solution. You follow? But here's the thing. Look at this family of solutions. Is there any choice I can use to get this to equal 3? In other words, is there a value of c I can plug in to get just 3 out? Well, let's see. If there were, note the subjunctive, I could multiply both sides. These would drop out. And if there's one thing you want to remember for differential equations, is that e to anything is always what kind of number, folks? Yeah, I mean, yeah, well, it's never 0. Yeah, for any finite number, it's never 0. Yeah. If x runs off to infinity, then it goes to 0, but e to anything is never 0. So what does this mean? I have a solution. So y equals 3 is a solution. However, I cannot recover it from this family. So even though this family captures infinitely many solutions, it does not capture them all. So this is not the general solution. We've missed at least one. Now, I don't want you to lose sleep over this, because it's like, oh my, it's the end of the period here. We got like 5 minutes left. I don't want you to like wake up in the middle of the night thinking, how many other ones did we lose? Okay. How many other ones did we lose? This is the only one. This is the only one you can't get from this formulation. All right? You can. This represents all the other ones, so don't freak out about that. But the point is, that's not the general solution. We will have a method next week to help us solve this equation, and in doing that method, we'll be able to make sure we capture all of them. Okay. Yeah, I think we're just going to call it there. I do want to point out. That's a great question, Zeron. Not that I'm aware of, unless you allow like points at infinity. Let's talk about Blackboard here, because I do want to point this out to you, because I might have forgotten to do this in the video. Did I mention test 0 in the video? I don't know if I did. If you pop into Blackboard here, under assessments, we got the test 0 in here. So please, download this, print it out, and upload it. This will give you practice on how I want things submitted to Blackboard. If you've had me before, this is the classic background information sheet, honor code, and then the syllabus quiz. All right, so make sure you do that. This is how I'm going to record the federally mandated financial aid attendance thing. So since we're a public school, we get state funding. Whether or not you personally get financial aid or not doesn't matter, especially for these online classes that I teach where only half of you can tune in at any given time. It's really important that you do this for me. Okay, everything else in this class is going to be due like Mondays, but I think Wednesdays, but this one is due Monday, right? Is that Monday? No, what's the 24th? No, it is, no, this is due Wednesday. No, yeah, oh, that's right, because it's Wednesday before noon, so that works. Wednesday before noon is fine. Okay, make sure you get that in. Tomorrow we're going to talk about, we've talked about having these parameters. How do we pin them down? That's initial and boundary value problems. And then we'll talk about how to visualize them. So we got a nice little application we'll link to visualize these things, because first order equations talk about slopes. And then we'll head in and start talking about our first, we'll actually start talking about solving differential equations with our first big type of equation called linear. And if you're in linear algebra, we're already getting into linear equations starting tomorrow. Okay? So I appreciate you tuning in, folks. If you're out and about today, be safe. It's extremely cold and we got some snow falling. Take good care, and I hope to see you back here tomorrow.